A study named The Big Defreeze of the Universe. Identity Stem Waves and Complex Forces in Cosmology by Mohammad Hasan Algarhy proposes that the universe originated from a reverse mechanism of the Big Freeze, beginning as a tiny collective quantum wave, the identity stem wave of the universe, ISWU. This wave accumulated energy forming identity stem waves of matter, eventually leading to a super-symmetrical crystal structure. The study introduces the concept of the Big Defreeze, wherein the universe emerged from a frozen state at nearly absolute zero temperature. Additionally, the research explores three new fundamental forces, termed the complex forces, which could explain universal expansion and symmetry-breaking mechanisms. It also suggests a methodology using Bose-Einstein Condensates to test the proposed framework, offering new insights into cosmology and quantum mechanics. The research aims to propose a mechanism that explains the conditions preceding the Big Bang, the formation of identity stem waves, and the role of newly identified complex forces in shaping the universe. It presents a significant advancement in cosmology and quantum mechanics by providing a novel framework for understanding the early universe and fundamental forces. The proposed model could offer new perspectives on the origins of matter and the expansion of the universe. The universe heading towards absolute zero. As the universe is expected to become cooler and cooler, heading towards absolute zero, this study proposes that all matters, even if they are not a boson or ideal gas, are expected to form Bose-Einstein Condensates, also known as BEC. The fermions problem is addressed in this paper as well. When a gas is cooled down, the atoms slow down and their energies decrease. Due to the quantum nature of atoms, they behave as waves that increase in size as the temperature decreases. At very low temperatures, the size of the waves becomes larger than the average distance between two atoms. At this very low temperature, all of the bosons can have the same energy in the same quantum state. They all form a single collective quantum wave called a Bose-Einstein Condensate, or BEC. The study proposes a scenario called the Big Defreeze at the beginning of the universe, where all matters started with a single collective quantum wave, which could be referred to as the identity stem wave of the universe, or ISWU. In other words, the universe was in a frozen state at almost absolute zero temperature and potentially shrunk into a very tiny collective wave. The study proposes that our universe started with a reverse mechanism to a modified Big Freeze scenario. It began as a tiny collective quantum wave, which could be referred to as the identity stem wave of the universe, or ISWU. This stem wave started gaining energy, leading to fluctuations behaving like a string, forming what could be referred to as the identity stem waves of matter, leading to a super-symmetrical crystal with no well-defined boundaries. The identity stem waves of all elements started forming and interacting. This is so far pretty much what is generally expected anyway. If all matters, even if they are neither a boson nor an ideal gas, were smashed and shattered into their elementary particles, and these elementary particles, or more accurately, fluctuations of waves, started cooling down to degrees close to absolute zero, forming Bose-Einstein condensates. This BEC or quantum wave would act as the blueprint or the identity stem wave of this matter. The frequencies of these identity stem waves, or ISWs, are comparable to the temperature at which they form BECs. This study proposes using the Fourier transformation to test and measure the mechanism of forming the ISWs as spikes or fluctuations. It indicates that for the ISWs of all matter, the winding frequency is comparable to the ISW's frequency except for helium. The winding frequency is expected to be 299,789,000, 12 times the frequency of helium's ISW, which suggests a symmetry-breaking mechanism. This mechanism breaks the symmetry of the super-symmetrical crystal, leading to an explosion or a Big Bang with a value comparable to the speed of light. This study suggests that the universe began in a frozen state, heated up to initiate the Big Bang, and is gradually cooling down again. This proposed mechanism could help us understand the time frame of forming identity stem waves of all elements. These identity stem waves can lead to what can be referred to as the Big Defreeze grand spectrum, from where we can determine the identity stem waves of all elementary particles and how they were born. A suggested methodology for experimental validation would be shuttering particles of two periodic table elements in the cold atom lab and observing the reactions, including the potential formation of two identity stem waves and how they react. Understanding the identity stem waves ISWs of matter, basically how matter was born, how the ISWs of different matter interacted with each other, and the time frame for that could help us create hybrid matter. The universe's end and beginning are intrinsically linked in many cosmological theories. If we look closely at how the universe might end, we can gather valuable insights into its origins. One of the proposals of the Big Defreeze is that the universe is going to end the same way it started. So, if we know enough accurate information about how the universe is going to end, we will have good information about how the universe started, and vice versa. If we follow the logic that suggests that the universe will end the same way it started, as proposed in this study, then what would be the most likely scenario? The intuitive answer would be the Big Crunch, as the universe would be back to a dense, hot, and compact state, a lot like the state that preceded the Big Bang. Yet our most recent observations show that the expansion of the universe is accelerating. This means that the Big Freeze or the Big Rip is more likely to happen depending on the strength of the repulsive force or the amount of dark energy. Whether we consider the particle as a collapsed wave function, or a quantum excitation of a field or a vibrating string, the idea of the Big Defreeze suggests that when all matters are shattered to their elementary particles, even if they are not bosons or ideal gases are expected to form Bose-Einstein condensates, the atoms will slow down and their energies decrease. Due to the quantum nature of atoms, they behave as waves that increase in size as the temperature decreases. They all form a single collective quantum wave, a Bose-Einstein condensate, BC, which could be referred to as the ISWU identity stem wave of the universe, ISWU. So basically this is greatly compatible with what the Big Rip suggests, where the matter that makes up the stars breaks into tiny pieces. Even atoms and subatomic particles will be destroyed. The Big Defreeze suggests that the shattered or destroyed atoms and subatomic particles form the BCs and the identity stem waves, or ISWs. The Big Defreeze is compatible as well with the Big Freeze in the part related to the heat death of the universe. The Big Defreeze suggests that galaxies and objects within them would be shattered to their elementary particles due to the Big Rip, and then frozen to their Bose-Einstein condensates or identity stem waves due to the heat death of the universe, and not in the form of frozen, lonely, separated galaxies as suggested by the Big Freeze. In other words, the Big Defreeze suggests that the state that preceded the Big Bang was an initially small, compact, and frozen state, and then it started gaining heat and energy. The identity stem waves, or ISWs, of matter proposed in this study could be considered a type of Bose-Einstein condensates. They are basically matter waves. The idea of the Big Defreeze puts it in the context that these matter waves were formed for all matter at the beginning of the universe before the Big Bang and inflation. Achieving and testing Bose-Einstein condensates involves understanding the conditions under which they form and the methods used to observe them in a laboratory setting. If you want to achieve Bose-Einstein condensation, you have to cool down a gas to micro and nano Kelvin temperatures until the de Broglie wavelengths are comparable to the spacing between atoms. The matter waves overlap and start to oscillate. The de Broglie wavelength depends on temperature. The distance between atoms depends on density. So the transition to Bose-Einstein condensation is characterized by a combination of temperature and density. Wolfgang Ketterle described watching how a condensate formed for him, like how nature is giving birth to something very fragile, but we were able to observe it in its natural environment. The principles of laser cooling are pretty simple. You shine laser light on atoms, the atoms scatter light, and if you play some tricks, the light which is scattered or emitted has a shorter wavelength and is more energetic than the absorbed light. The scattering of light removes energy from the system, and the system cools down. There are two types of magnetic traps. Some have a pointy potential and a linear V-shaped potential. Others have a round potential at the bottom. Those traps are more tightly confined. Interference between two condensates allows you to photograph matter waves directly. The interference is clear evidence of the wave nature, where you build two condensates, so you basically have lots of atoms in the ground states in each of the two traps, and then you turn off the traps, let them go. Then you can measure the distribution of atoms as a function of position. You see fringes in the atomic density because the two condensates were interfering with one another. What determines the spacing between the fringes? There is a de Broglie wavelength for the atoms, and there is a de Broglie wavelength difference between the two condensates. This is quantum interference between atoms. The optical trap could be used as a transport mechanism for Bose-Einstein condensates again, thanks to Wolfgang Ketterle and his colleagues. They now can form a condensate in one vacuum chamber, then focus the laser light on it and translate the focus by around 40 centimeters and carry the atoms into a new chamber, so they can deliver condensates with precision through pinholes and put condensates into new environments like microtraps and resonators, for example. The fermions problem and the Big Defreeze. The fermions problem. The Big Defreeze proposes that all matters, even if they are not bosons, will form Bose-Einstein condensates when shattered to their elementary particles and cooled down to near absolute zero. Fermions might have a different opinion. We will have a fermions problem here because their quantum behavior would be different. How would we solve the fermions problem? The answer to that is that the Big Defreeze is dealing with the beginning of the universe. Basically, there were no bosons and fermions. This means that the quantum behavior of fermions is not to be considered at this stage. The Big Defreeze suggests that there was the collective identity stem wave of the universe ISWU. Fluctuations and interactions started to happen to lead to the ISWs of matter and the symmetry breaking by the identity stem wave of helium. All that does neither have fermions nor their quantum behavior. One of the predictions of the idea of the Big Defreeze is that the universe will end the same way it started. Won't we still have fermions towards the end of the universe? The answer is that in the case of the Big Rip, even the subatomic particles would be destroyed. They will lose their properties, including the quantum behavior of the fermions. But they are expected to maintain the behavior of forming BC-like matter waves, which we refer to here as identity stem waves ISWs. So, after the subatomic particles are destroyed in the Big Rip scenario, the universe will be heading towards heat death and near absolute zero temperature, where the destroyed subatomic particles will start losing energies and forming BC's ISWs, which will eventually shrink to again a collective identity stem wave of the universe ISW.